transcription as well. There it is. Okay, so the transcription is on, and if folks have questions, you can raise your hand and type it in the chat, and I'll try to flag it as we go along.
My own audience has decided to start playing in the background, so that's.
Mine too. No, not yet. Well, let's not jinx it. Okay, you ready? Let's get started, eh? It's 3:33, an auspicious number. Good afternoon, everybody. Welcome to today's Codebreaker, our first Codebreaker of 2022. As you have noticed, I am not Matt Evans. I am instead Hillary Fischler, the Research and Education Specialist for CAES. And Matt and I are kind of sharing the Codebreakers for this part of the year. Today, we're welcoming Dr. Jackson Harter. He's coming to us from his house in Idaho Falls. He's a staff scientist in INL's NS&T Reactor Physics and Analysis Group. And he mostly works on neutronic and thermomechanical analysis of different microreactor projects, as well as electron, phonon, and coupled electron-phonon transport, specifically for the MOOS framework. And he's also contributed to the Griffin radiation transport application as well. His research topics and interests include phonon and electron scattering, phonon and thermal electron heat transport, Boltzmann transport equations, and interfacial heat transport and microreactors. Prior to his position as a staff scientist at INL, he got his PhD from Oregon State University's Nuclear Science and Engineering program, Go Beavs, and interned at INL's Reactor Physics and Analysis Group, Fuel Modeling and Simulation Group, as well as Los Alamos National Laboratories Fuel Modeling and Simulation Group, and has worked with NuScale Power on probabilistic risk assessment. He is the recipient of 2 LDRD grants, one of which he will talk about today. So, as I said, if you have questions as we go along, you can raise your hand. You can type them in the chat box. And yeah, Jackson, take it away.
Thanks for the introduction, Hillary. So thanks all for being here today. My screen should be sharing. You should be able to see my slides. Can you see them? We good?
Yes.
Okay, great. All right. So the title of my talk today is Data Visualization and Predictive Simulation Techniques in Nuclear Fuels Research, Modeling Microscale Heat Transport Using the Applied Visual Laboratory. It's a real big mouthful. Basically, the kind of goal for today is that I'm going to communicate a little bit about some of the research that I've done, research that others have done, and then how intra-laboratory departments can work together really well to sort of help communicate to the public, but as well as to each other, the nature of our work, where some people may not have certain knowledge of certain topics. Visualization is a really nice tool to be able to communicate those effectively, because most of us are able to sort of see phenomenon with our eyes rather than just looking at a page full of numbers and trying to understand something from there. So first off, a little introduction about me. So I am 37. I grew up in Oregon. One big thing about me is I'm not really a traditional scientist or an engineer. I didn't really focus on school growing up. Throughout middle school, high school, whatever, call it what you want, I was distracted and interested in other things besides school, namely cooking. So when I was in high school, I started working in restaurants and then ended up going to culinary school after that to leave my small town. Ended up working in San Francisco and in Portland, Oregon, in multiple restaurants, and then actually teach in culinary school for a while afterwards. It wasn't until 24, 25 when I realized that, hey, I can't really do this forever. What else do I like? And long story short, nuclear engineering was something that I focused on. I'd heard about it for a long time and was interested in nuclear power because I believe in clean energy and I believe in trying to leave the world a little bit better place than where we started. So did research, and then I enrolled at OSU in 2009, and I got my doctorate about 10 years later. As Hillary said, I did intern here quite a few times, quite a few summers, but then hired as staff in January 2020. I've been at home since March, since the start of the COVID pandemic, and I've got a lot of various interests, but they all kind of lead back to here today. So what we're going to talk about. So going to kind of go over some of the motivations of why we want to do microscale heat transport in the first place and sort of explain to you what that is and what its purpose is. And then, of course, as was mentioned, the kind of focus is phonons and thermal electrons, as these are the energy carriers in materials, in most solid materials. Then we're going to kind of switch a little bit and talk about why visualization is important and why collaboration between interlaboratory entities is really important as well. So the primary motivation is that, thermal properties dictate thermal performance. As I've sort of shown here in this pictogram, if you sort of think about things on an atomic scale, atom by atom, how does it make up something that's so small? How do we use those phenomena that happen at the atomic scale and leverage them in something that's sort of at the engineering scale or the macro scale? And I'll use those terms sort of interchangeably throughout my talk, the engineering scale and then macro scale. And by that, I just mean anything that's sort of, millimeter, centimeter, and larger. So things that we can kind of see and touch in the real space in real time, and work with either by forging in some sort of steel mill or build in a laboratory or build in a shop. These are the kind of things I talk about and what it means to be macro scale or engineering scale. So the thing is, as you might expect, the way the world works is that everything's sort of interconnected. I don't want to use the analogy of, butterfly flaps its wings and a tornado appears in Kansas somewhere. But if we think about sort of the scale of phenomena from the very small to the large, there's so many interconnected quantities that it's important to sort of, as we have progressed in our technological advances to get stronger computers, developed new methods, algorithms, and softwares, we can start to link these things together. So if we look at this equation, and I promise you this is going to be the only equation in this talk. If we look at this bottom equation here, we have this K, that's kappa, that's our thermal conductivity, and it's equal to some equation. And then we have it equal to some equation up here, and then it's involved in this equation up top. Now, these three quantities are connected through scale. The quantities of V and tau, and quantities of Q there, those are things that we can predict on the micro scale, so the atomic up to nanometer scale. Now, if you're not familiar with nanometer, micrometer, or whatever, that's okay. You can think about a nanometer as, about a thousandth of the diameter of a human hair. So really, really tiny stuff. And these are the phenomenon that microscale heat transport addresses. But the other thing to think about and to understand is that all these phenomena that happen at the microscale, the macroscopic applications used, CPU processors, anything reactor scale, anything large scale, all these things are affected by what happens and what changes at the microscale. And during the course of this talk, we'll kind of discuss, what that means and how those changes affect everything. So, in general, we talk about, I talk about, heat transport and heat phenomena, but, because I'm a nuclear engineer and because I do work for reactor physics, one thing that sort of motivated a lot of my work back when I was in grad school is the fact that these microscale heat transport phenomena can really affect the way neutrons move inside of nuclear reactors. So one thing that I like that is a great way to discuss this is sort of this neutron interaction cross-section or cross-section. This cross-section is really heavily affected by changes in temperature. And I'm not going to get into some of the sort of the low-level physics, but you can imagine if you think about an atom has a target space, a cross-section. And this target size changes based on its thermometer, based on its temperature, excuse me, sort of much as the way this pufferfish might change its size if there's a predator nearby. And it has these things called resonances. And these resonances, they essentially expand and contract based on temperature. It's a little more complicated than that, but that's really the thing to take away from this. The other phenomenon to consider is density, right? So density also changes with temperature, right? You can think about air expanding and contracting, or water, how water sort of begins to have its own natural circulation based on temperature changes, right? So one of the motivators for this work as well was trying to help understand and predict phenomena in nuclear fuel more. And through doing that, we can actually lead to safer nuclear fuel if we can predict its operating range and then its accident tolerances as well. Now, in working with microscale heat transport, I wasn't just working with nuclear engineers. I actually I had two advisors when I was in PhD, and I still work with them now. One was a nuclear engineer and one is a materials scientist. And through interactions with the materials science group that I worked with, I got involved in trying to help predict properties and performances in thermoelectric devices. Now, a thermoelectric device, it leverages something called the Seebeck effect, which is essentially where if a temperature gradient or temperature difference is applied to some certain material, it'll actually generate an electric current. And these things, we can think about this as, if we want to sort of use this effect somehow, we can recycle waste heat. So if you think about industrial processes, things like generating hydrogen or manufacturing, there's a lot of heat that's generated with these processes too. And so if one were to put on essentially parasitic thermoelectric devices to harvest energy from this waste heat, you can actually sort of, reduce your load on the environment and actually and then power other processes in that plant. Not only that, a big topic these days, and sort of, well, has been for a while, but one sort of major motivation is remote nanosensing. Now, the one concrete example I can give you are actually car manufacturers, automobile manufacturers. So they will run engines and test engine performance, and they will throw on these nanosensors on their engines, on their car engines, and the heat generated by the car engine will actually power the sensor and then reduce or remove the need for any kind of wire. These are wireless transmitters. So that is one example of how a company, this actually was Mercedes-Benz, that uses these nanosensors to sort of recycle waste heat from their engines. Now, everyone is really excited these days about quantum computing, and I think we have kind of a ways to go with that. But as you all probably know, any kind of computing device is giving off heat, and we have to either harvest that heat and remove it in a way that allows that device to operate normally, or also recycle it. But quantum devices need to be kept at very cold temperatures, and so managing the thermal power or the thermal output from those is really critical. And one could also use microscale heat transport to simulate that. Now, we all have these, I'm assuming most of us probably have these nice, fancy, thin cell phones these days. So, one of the chief, I guess, motivators behind this back in the 1990s, there's a man named Aaron Majumdar, who's still around and still does a lot of work with one of the government agencies. I think it's DARPA or ARPA, I think he works for. But the point is, we use this microscale heat transport to reduce the need for expensive experimentation. And what that means is, if through modeling and simulation through computers, you can build some geometric object like a CPU or a microprocessor or some transmitter, and then run a simulation with some temperature gradient applied, and you can figure out, based on your simulations, how to narrow the scale of your experimentation needs. And so by doing this, you can increase the speed of development of these new materials and devices. And it's not just devices; it's we search for materials with interesting phenomenon. And I'll get into that a little bit later, but the point is, by leveraging phonon and electron transport, we can do this, and we can sort of help bring these devices to market and to make them useful for people. Because, while a lot of this work that I've done and kind of continue to participate on is fundamental in nature, I really like seeing devices brought to market and technology brought to people that can actually use it and it be useful in my lifetime. So how do we do this? So it's a mouthful, but the mechanistic prediction of thermal properties is all based on conduction at the atomic scale. So we have these two particles inside of materials, electrons and phonons. Now, electrons will carry energy in metallics. They're the dominant carrier of energy in metallics. And then phonons carry it in dielectrics and insulators. And dielectrics, something like a semiconductor, a silicon is a good example. Now, these pictures sort of explain, the way these things work, the physics of these things. So when we look inside of materials, on the left here, you see this, this confluence of lines, and these are grains inside of a material. Excuse me. And within these grains, we have carriers, could be phonons or electrons, but these scales, they shrink, okay? Now I'm going to get up to this third pictogram here, and this is lambda, and that stands for the mean free path, and it's the average distance a carrier will travel before an interaction. And L stands for length, so length of a grain, length of a simulation cell. And the thing is that the physics of heat transport changes as you go from small to large. There's an idea and a concept called thermal length, and when the mean free path, or the average distance a particle travels, is on the length scale of the material. So if I have a phonon with a mean free path of 25 nanometers, and I have a sensor that's 25 nanometers long, that phonon on average will travel across that material without scattering, without having one interaction. And we call that a ballistic phonon. And as you scale up, and let's say we increase the material length, so let's say it's 5 times or 10 times the mean free path of the photon's got to travel a lot further, and it's going to scatter off the material, and it's going to actually deposit some of its energy in the material and lose some of that. And so we call that diffuse scattering. And that essentially is acoustically very thick. And so it just takes the phonon a much longer time to travel across the material. Now, electrons have a very similar phenomenon, but on average, you can think of their behaviors as doing the same thing, scattering and traveling across the material. But electrons tend to have a much shorter mean free path in certain materials than phonons do, and so they'll scatter a lot more. So one thing you'll hear me talk about a little bit more today are defects. Now, when I use the word defect, if you can think about a perfect lattice. So if we look at this bottom picture here and look at this where I've sort of, hovering my mouse over here, this is a crystal structure. Within this crystal structure, there could be an atom out of place, there could be extra atoms, there could be a vacant atom. So the idea is that a defect is just that, defect in the material. And it turns out that if you had a perfect crystal or a perfect material, thermal conductivity, which is essentially how well a material carries heat, thermal conductivity would be infinite. That's the presence of these defects, because in our actual world, nothing is perfect and no material is perfect. It's the presence of these defects that actually gives rise to a finite or limited thermal conductivity. And so a lot of work is done in these areas with trying to manufacture materials that actually maybe we could take advantage of those defects. Maybe that changes the scattering behavior of a phonon or electron. But either way, the defect presence lowers the heat flux and thermal conductivity. Now, why is this important to nuclear engineering and to microreactors exactly? Well, when nuclear fuel undergoes nuclear fission, right? So when a neutron splits an atom of uranium, a bunch of heat and energy is released, but also byproducts of that uranium are released as well. And one thing that is really important to reactor control is xenon. And it turns out, and we'll kind of get into this in a little bit. It turns out that xenon is actually a pretty big scatterer of phonons and lowers thermal conductivity in nuclear fuel by quite a bit. And we'll get into that later in the talk. So why have I said all this? The reason that I want your attention, and the reason that I keep talking about this, is that over the last decades, even century, I mean, scientists and independent folks have done research on materials and tried to figure out the best way of manufacturing something, of simulating things. But the limiting factor is actually the way we understand materials at a fundamental level. We've done a lot of work, at the macro scale. So a lot of equations, a lot of measurements, a lot of simulations on things that we can see, but it's the things that we can't see. It's the physics and the behavior of these particles at the nanoscale and the atomic scale that actually control everything at the macro scale. So understanding the fundamental behavior of materials is what we need, is where science and engineering has to go in order to manufacture, in order to control, in order to bring about technology that actually is very useful. So I got into phonons a little bit, but I want to talk about them a little bit more now. So you have some material sitting at rest. For an example, let's just say a brick. We sort of, most folks I think can understand what a brick is. Brick is a building material. It's great. It's a ceramic. If you have a brick at rest, the atoms in the brick are vibrating. The atoms in the lattice are vibrating. And this is always happening because nothing is at absolute zero, temperature-wise. Even at room temperature, there are vibrations taking place. Now, phonons don't exist without some displacement or something arising. So to displace temperature, let's say we apply a hot and a cold end to this brick. When I apply this heat difference, phonons are generated across the brick because the heat is making the atoms vibrate more, okay? So you can think about these as waves, and I know I use these quantized words a whole bunch, but essentially when these atoms vibrate, they give off phonons, and they give off these waves. And we simulate them as particles. Wave transport is not sort of the things that we do at the engineering scale or even the microscale. That's more atomic scale and not sort of what we do here with this particular research. And they follow something called the Bose-Einstein statistics. And this is essentially it's a distribution of how many phonons exist at a particular frequency and at a particular temperature. And it's not too important to remember that, but that's just the way essentially their equilibrium behavior is dictated. Now, if we get into electrons, we sort of simulate these a very similar way, but electrons are not generated from these displacements. Electrons already exist in the material. There's a finite number of them, and they're also moved through thermal and electrical influences, heat differences as well, and voltage differences. And they follow something called the Fermi-Dirac statistics, which there's some pretty stark differences. But what I want you to understand is that these essentially can be thought of as reservoirs describing their distribution around a particular spot in a material. So I want to, I've talked about this a little bit before, but I want to sort of show you visually what the scale regimes in heat transport are. So, if we think about things on the pico to nanometer scale, these are down to the atomic scale. There are a host of methods and algorithms and softwares that simulate these behaviors down to that low scale. As you sort of rise up in scale in sort of length and time, we get to different equations and different methods of transport. We're going to focus today on what happens when you apply the Boltzmann transport equation to these methods or to these materials. But we actually we want to influence what happens at Boltzmann transport from everything that happens with these molecular dynamics, density functional theory, and these things. And this is not going to sort of get into the low science of these things, but we can leverage these methods and codes and algorithms to actually give us data at the atomic scale that we can then use at the larger scale. And I work with several folks who actually do these things for me. When I find out that, hey, I need to figure out, I want to run some simulations on, silicon, or I want to run them on uranium. I want to have people that can give me information at the atomic scale that I can leverage at my scale, essentially. Now, the reason that we sort of want this scale bridging gap, and it's the importance behind it, is that, while we call this MD or DFT, while these MD and DFT methods are really, really accurate, and they can simulate lots of cool things that are happening, even more than we can at the Boltzmann transport scale, because they're so computationally expensive. And what I mean by that is when we run simulations, we use these vastly powerful machines called high performance computing. We have them in INL, and they exist everywhere in the world. An expensive simulation is something that takes up a lot of processing power and a lot of time, and we don't really have a lot of time. And there's a finite amount of both of those things. So while these methods can give really good information, they're unable to simulate large systems of atoms. So if you think about a cubic centimeter of copper, there might be 10 to the 27 atoms in that sample of copper. And these methods can really only do up to about 100,000 atoms, like 10 to the 5, 10 to the 6 maybe. So if you want to use anything And if you want to actually apply anything at the macro scale, the engineering scale, there's got to be some in between, right? You can't just go from, trying to simulate using these methods and simulating a 100,000 atoms in a box to, 10 to the 27 atoms in a box. It's just not possible. I mean, it is, but it won't, not possible in this year or next year. So that's where this work comes in, as we sort of bridge the gap in between the very small and the large. So the way we do this, this is sort of a sample workflow of the way one of these simulations might go, is that we use these, these ab initio, from atom simulations. These are run on various materials, and I'm going to get into some specific examples later on, but I'm just going to kind of go over the basic methodology now. We run these simulations, data are generated via, these things called dispersion relations, the density of states, relaxation times. And what these are, a dispersion is a relationship between a phonon or an electron's wave vector and its frequency. And it just allows, materials have these, semiconductors, and actually anything really has band structures. And the dispersion relation can kind of show off and help show off some of these band structures within the atoms, or within the materials, excuse me. And from dispersion, we can find out things like, well, how fast are these things moving? What's their average speed, of the electrons or the phonons in this band? The density of states is sort of an area in inverse space that these particles occupy. They're shells that are sort of if you think about a sphere, shells within a sphere at different energies and frequencies. And then relaxation times are really, excuse me, I really should have put scattering rates, but the relaxation time is sort of the average distance, or the average time it takes between an event, a scattering event. So, if we think about how a good example might be, if you're a runner and you're running some marathon or let's say you're a hurdle sprinter. So you're running hurdles, and the hurdles are obstacles you're trying to get around. You're trying to jump them. Maybe you trip and fall, but the idea is that these things slow you down. And that's, you could make the analogy that those are just like defects. And so when you scatter and hit something, that's the time it takes for you to get to that obstacle and scatter off it or change direction. So one big important thing to grasp here, and this is going a little bit deeper than we need to, but when these properties are generated by these simulations, they're all generated assuming that nothing is moving. So atoms are not vibrating. I said earlier that everything is vibrating because it is some temperature. Well, they use the assumption is used that materials are at 0 Kelvin, so atomic motion has ceased, and they can sort of perfectly figure out what the spectra of phonons and electrons might look like. So that's something to take into account, and we have to sort of either use a grain of salt when we look at the outputs of these things or when they come out, or finally in the last 10, 15 years, methods have been developed to adjust these properties from 0 Kelvin to temperatures that we work with. So that's what we use now. So we use something, I'll get into this flowchart a little bit here, but once those ab initio simulations are going, we then use codes called PhonoPy and thermoelectric. And these things essentially parse and convert the data from the ab initio simulations to things that are usable in a transport method. All right. So once we have these things, they're passed to the transport codes, that's where I come in. And we use the transport codes, and I'll talk about that a little bit later as well. And we pass this into our Boltzmann transport equation simulations, and we get out things like heat flux, thermal conductivity, temperature distributions, and heat capacity. And these are all useful quantities that we can use at the engineering scale. All right, so because we have informed our codes from the atomic scale, and now we run them in a Boltzmann transport equation where you might have things on the millimeter scale or the microscale, so 10 to the minus 3 millimeters and 10 to the minus 6 for microscale. We can then use these, and through validation and verification efforts, we actually might be able to apply those to the macro scale. So I talked earlier about how different the physics are between nanoscale or smaller and then the macro scale. And this is to show you directly how that is. So what we're looking at here is a graph of thermal conductivity in silicon. Now silicon, the length goes from this actually, it's about 5 nanometers, up to 10,000 nanometers. So we go from the very small to about 10 microns, or 10 to the minus 6. And what you're seeing here is that due to the way phonon scattering changes in this material, the thermal conductivity increases as we get larger. And the reason for that is precisely it can be a little murky, because it's like, well, you think silicon is silicon is silicon. Why would the heat transport, or why would the thermal conductivity change based on how big it is? I mean, that doesn't make any sense. And it didn't for a while. It took me some time to understand that. But what happens is, so if we have some strength of phonons, okay, we have a hot source and a cold source. What's happening is the hot side essentially is a phonon emitter, and so is the cold side. But the hot side phonons are stronger and at a higher energy than cold side phonons. And what happens is, the closer these things are together, so the smaller in scale the material is, the hot phonons and the cold phonons will sort of interact, and they'll collide. And they will actually scatter more. And by increasing phonon scattering, we reduce heat flux, which in turn reduces thermal conductivity. So as you go from small to large, there's less chance for these things to interact with each other and to sort of change the sources at the base, or at each hot and cold side. And so phonons can travel further and not scatter as much, and therefore have a higher heat flux and then increase thermal conductivity. So that's what you're seeing here in this plot, is that as we change size and get larger in size, thermal conductivity gets larger. And eventually, if you did that out to, centimeters to large scale, that you actually max that out. This is what is called, this is an asymptote. So it'll eventually kind of level off and go to a not constant value, but it'll look like a flat line essentially. And we see something very similar with electrons. This is electron thermal conductivity in silicon as well. So as we change length from about 5 to 150 nanometers, we see the thermal conductivity increase and then start to level off. Now, there's a big difference in thermal conductivity between electrons and phonons in silicon, because phonons are the dominant carrier. It's a semiconductor, and phonons carry the dominant portion of thermal energy, and where electrons won't, as you see based on the scales here. Yeah, let's see here. That's one side. Yep. So one thing I want to get into that's really important, and it's a phenomenon that every material has, is something called thermal interfacial resistance. So if you think about the inside of a material, let's say you have a block of copper and silicon sitting next to each other. All right, well, if you apply heat to one end, it's going to go all the way from, if you apply heat to the copper end, you're going to get a heat change on the silicon end because of thermal diffusion, and and the whole thing's going to heat up. The thing is, though, the interface is very interesting. Phonons will actually experience an effect at a physical interface compared to a particle like a neutron that just passes through everything and only cares about the atoms in the material, whereas the phonons actually care about the interface itself. And so if we look here at this picture in the bottom right-hand corner, this is a slab of silicon, and we have the hot side on the right and the cold side on the left. And if we model this interfacial resistance, there's a temperature jump here right at the center. You would think that, like, okay, well, there's no interface. If it was just one homogeneous block of silicon, you'd have transport all the way through in this smooth line, right? This pink line right through the center. But if instead you have two blocks of silicon next to each other, and there's a difference there in a physical gap, or a physical interface, there's actually a temperature jump from left to right. Now, it's a really fundamental phenomenon that no one has a really good answer for. The model that's applied here is called the diffuse mismatch model. It was developed back in the 1980s. And it's okay. It's not great, but it's acceptable. What really happens is a topic of intense debate among phonon transport researchers. What we actually think might happen is, if we think about this graphic here, if this is a slab of materials, some different material left and right, there's this interesting effect that happens at the very center here when they collide, and they're influenced at the center and the phonons change their behavior based on the differences of the essentially the phonon spectrum in each material. So, when I was talking about phonon dispersion earlier and density of states, well, for something like silicon or germanium, they're different. The dispersions are different, and so are the density of states. And so I actually think, and I haven't proved it yet, but that's one of the things I work on, is trying to prove that there is some interesting smearing effect between the two materials at the interface, where if the atoms are if the materials are smashed together, there's actually some material diffusion going to the left and to the right, and that there's actually a mixing or a smearing of both silicon and germanium, or material A and material B at the interface. So you couldn't actually say that it's just A and it's just B. It's some interesting mixture. Some interesting mixture at the interface itself. Now, to verify we were doing this at least somewhat right, we did this. We just sort of modeled our work against a bunch of stuff that was done about almost 10 years ago, and it turns out it matched up pretty well. And what we're seeing here, if we look up in the upper right-hand corner, in this small, in the B figure, we think about a square of germanium with a small square of silicon in the center, and we're going to put a temperature difference on the left and the right-hand side. So let's just say across that small distance, 1 degree Kelvin. Now, 1 degree Kelvin is not that much at our scale, but 1 degree Kelvin across a distance of 300 nanometers or 600 nanometers is actually quite large. And what happens is as you look at the material, and if we're looking at the bottom right-hand graph here, if you start from the left-hand side, you have heat diffusing across the material, and it interacts with the silicon in the center. And because the silicon has different properties, the slope of the heat, this is actually temperature we're looking at, the temperature slope and the temperature difference changes in the silicon and then sort of resumes back its normal behavior, or its germanium behavior, when it reaches the germanium. All this is to say that if you have materials embedded within each other, you're not going to expect a smooth heat difference all the way through from left to right. You're going to sort of see jumps and gaps and slips as materials change. And these are important to keep in mind, because a lot of the new fuel for microreactors, microreactors, uses triso fuel, and I'll get into what that is in a little bit. But this fuel has layers in it. It's got a uranium center, but there's also layers of carbon and various forms of carbon on the outside of it. So knowing how to predict these things and knowing how to model them is actually quite important if we want to predict the way this fuel performs. So now we've come to code development. Now, what is, all the efforts that have brought us here, and that's sort of the subject of the LDRD that I finished up last year. This was a seed LDRD. But myself and then my co-investigators, we spent time and developed methods for this phonon and electron transport at the Boltzmann scale. And what this does, in the code we actually named Boltzmann, it combines both phonon and electron transport with a bunch of neutron transport code that was designed in Griffin. And Griffin is a radiation transport code here that we use for a lot of things. Large reactors, microreactors, small modular reactors. And being as it is a neutron transport code, it has been and is export controlled. And a lot of the work with the LDRD was to actually extract a lot of the general purpose transport machinery and put it into Boltzmann, because Boltzmann is actually going to be in Moose. It's not there yet, but we're working on it. It'll be released this year sometime. And the idea is that Boltzmann is open sourced because Moose is open sourced. And we know, and we want everyone in the world to access our tools, because at INL we have designed these fantastic, not me personally, I've done a little bit, but the folks that have been here for a decade or more have designed these fantastic tools in Moose to simulate literally everything under the sun. I mean, you can simulate fluid flow in rock. People actually can simulate, when we think of hydraulic fracking for trying to get gas and oil to the surface, we're able to simulate what that looks like going through the materials. We can simulate thermal hydraulic flow in reactors. We can look at how laser welding can etch things onto surfaces. It's a really phenomenal code package, and if you're interested in modeling anything, it really has something for everyone. So that's sort of the purpose of this work was to not only develop methods for phonon and electron transport, but also to make them available or widely available to the public, because there are a lot of one of the sort of biggest hurdles that scientists and engineers face is that there are many people who want to run many problems. I mean, there's hundreds of thousands of scientists everywhere that want to do really cool, unique stuff. Someone might write a really interesting code that does 2 or 3 things really, really well, but other things not so well. Now, the bonus and the sort of what we have going for us here at INL with Moose is that it's maintained by professional coders who keep it at a certain software quality and are always adding new phenomena and new features to it. So it's a really nice way to model most things. And if you ever have questions, about that, you can always get in touch with me and I can point you in the right direction for those people. Just to mention my funding sources for this. So a lot of the work was done with the seed LDRD, and then the full LDRD is actually is doing a lot of modeling and simulation with phonon electron transport to model thin films of actinide materials. So we look at uranium and thorium. We were interested in some of the electronic phenomena that are happening within those and how they could be used used and then better understood as fuels for reactors in the future. So, it's okay. So now I want to transition a little bit, and this is where I'll get into examples of of what the code actually does. I want to transition to talking about visualization in scientific communication. So, as someone who didn't come from an engineering background, my parents and family aren't engineers. I didn't really know anyone who did that growing up, and I never really. It took me a long time, and it took me a lot of focus in my graduate work and undergrad work to learn math and physics and everything. And I do love it now, but I didn't. I didn't understand a lot of things that I would read as a teenager, as a young adult. I need to know. Numbers didn't really mean a whole lot to me. It's like, what does this even mean? And I've always been interested in the visual aspect of things as well, because I used to cook, and I when it comes down to plating or making things appealing to the eye, that's really, really important. And I know that's what people understand. So when I did my work, I learned how to use certain visual tools to communicate my points to people. Now, as it happens, there is this applied visualization laboratory here at CAES, the Center for Advanced Energy Studies. And I didn't know previously until I think it was November of last year, or maybe a little earlier. I didn't know it existed. And I could not be happier that it exists. I'll put it that way. So as it says on my slide, visualization helps to enable science. I think that it helps with our perspectives and inclusion because, again, unless you're visually impaired, and I am visually impaired a little bit, you can understand phenomena that someone points out in a picture much better than someone who gives you a table of numbers that's massive. And you're like, what do I get from this? I have no idea what this means. And this really helps us to communicate to our colleagues, to the public, to the folks that fund us. And because certainly, people that are in charge, maybe they might know science in some area, but they might not know science in my area. And giving them a table of numbers doesn't really do much for them. But giving them a picture and then explaining what's going on in the picture is really, really useful. And one thing that it's not really part of this talk, but I'd like to get over it. I don't really like to think of people as resources. I think of them as colleagues that I work with. A resource is a machine, is a tool. And we work with these people, and they're our colleagues, and they're not just things to talk left, right, here. Everyone's got a story, and through getting to know people and getting to know their stories, you can do a whole lot of cool things and learn a lot of cool things. And that just happened to me. So I spoke with the director of AVL, John, and then one of the researchers, Nate, a while back, and I sort of got a chance to get a little bit better look at what AVL is doing and what it does. It's been part of CAES for more than a decade, and it's got a lot of really cool resources. If you ever get a chance, maybe hopefully when we sort of maybe returned to some sense of normalcy with the pandemic, getting a tour of the cave. And I don't remember exactly what the acronym stands for, but the cave is a super cool part of AVL. Scientists can give essentially these cave researchers their data, and this data can be translated into images and actually essentially a virtual reality world you can walk around in. I got to visit this when I was an intern back in 2016, and I was able to look inside of the ATR, the Advanced Test Reactor. There's a full-scale model of this thing that exists at the cave, and it's super cool. It's a computer-assisted drawing, of course, but you can navigate the reactor and like move things around. You can hide and show different things, and you can really see everything inside of this thing. The other really cool part, I don't remember the name of the cave they mapped, but there was this cave that's in Idaho. Maybe I think it's like Crystal Cave, I think. And they use these LiDAR scanners to get a sort of if you will, a topological view of the cave and map the whole thing out. And you can just literally walk around in this thing inside of virtual reality. That's one really cool thing they can do. Other things they have is they're able to sort of use augmented reality. It's called like a HoloLens. It's a Microsoft product, but essentially augmented reality is where I might be seeing my table right now, but I'll have goggles on that will display some. I could look at a model of a reactor through my goggles on my table. The staff kind of come from everywhere. There's some folks have different research backgrounds. Some folks don't. It's a really interesting mix. I think getting individuals is really it sort of takes all types of people, and it doesn't necessarily mean it's not necessarily a degree you go to school for. It might just be something you pick up along the way. A lot of the ways that people learn these visualization tools is they're interested in a problem, they want to figure out a way to communicate it effectively, and so there's a lot of work that goes on in the back end to learn these codes and to learn how to use them well, and that just happens to be a sort of like a notch on the notch in your hat, if you will, of things that of duties you can perform at a lab or at a job. And then of course they're funded through INL. So I spoke with Nate Woods back in the end of 2021 at the LDRD poster session, and he had explained to me that he was kind of going through each person's presentation, each poster session, and kind of just seeing what cool pictures they had. I mean, he's a visualization researcher, excuse me, at the AVL, and we struck up a conversation, and that led to some collaboration later on. And he was really interested in turning some of the data that I was presenting into something a little finer. And I thought that I had something pretty cool going on, but I had no idea what he could do and what AVL could do. So during the course of the Seed LDRD, I got invited to write a book chapter for this Advances in Heat Transfer series. And some of the things, the following images that I'm going to show you and movies that I'm going to show you are from data that was published in that series. But what he used that movie for that he made was to talk about essentially the capabilities of INL at the Supercomputing 2021 conference, which was pretty cool. So what is, where everything leads to this now. So we're going to talk about how we simulate heat transfer and thermal conductivity in uranium dioxide with xenon defects. Now, xenon, as I said earlier, is essentially the chief cause of why thermal conductivity in UO2 is decreased over time. So, just to give a plain example, if we have a reactor cycle means it's sort of one fuel cycle where we run a nuclear reactor for 18 to 24 months on a certain set of fuel, and as this fuel is fissioned, its uranium content goes down and its defect content goes up. The things that you sort of think about as nuclear waste aren't really nuclear waste. They're spent fuel, and they're actually really, really useful for the future, but that's another topic. But xenon forms in UO2 through fission, and xenon affects reactor control heavily and also reduces thermal conductivity. So if we think about it, if essentially after 18 months of a fuel cycle, thermal conductivity roughly goes down by a factor of 4 due to the xenon buildup. Okay, so while UO2 might carry heat really well at the beginning, at the end of the cycle, when they take it out and they replace it with fresh fuel, it's not carrying heat very well anymore. So this is a phenomenon I started investigating in my master's program and kind of led up to here now. And so, how do we model, how do we look at how phonons collide with xenon and how do they scatter and how does the heat transport affected around the xenon itself? So this box right here is a simulation cell we use in Boltzmann. The little bubble, the cluster in there in the center, are a snapshot in time of xenon atoms combining to form a bubble that then phonons will scatter off of. Okay, and this essentially this xenon bubble, we find out, and we'll show you, it's responsible for a ton of reduced thermal conductivity in the simulations. So the way this is set up essentially is, we assign a heat source to this backside of the uranium and the front side of uranium, and then we simulate how heat transfers or how heat travels down the center of it and how the presence of the xenon affects that heat scattering. The material properties for the xenon and the UO2, my friend Dr. Laura Oliveira at U Wyoming gave me all these material properties, the DFT, the molecular dynamics that I mentioned earlier. She and her group do a lot of that stuff, and so we work together to get these properties. So this is the first of a series of images that I want to talk about. So if you remember, there's a couple of different. This is from different simulations. Excuse me. This is from a single atom of xenon inside a cell of uranium dioxide. And so what's happening here? Now, if I just showed you the numerical output, it'd be a full table of numbers, and it'd mean some things to some people, but other things not so much to other people. And what we're seeing here is, if you remember this cell of UO2, there's a bubble in the center of it, and we have heat traveling from one side to the other. Well, in this simulation, heat's traveling from right to left, and the bubble here is being heated by the temperature difference. So this red area here and this blue area here goes from hot to cold across the bubble. That's one thing. The other thing we want to look at is the heat flux in the uranium. That's what we care about the most. So if you look at these lines on either side, this collection of lines here, we go sort of this orangish color is hotter and then blue is colder, of course, corresponding to the legends. And we see that close to the xenon, this heat flux, it starts to decrease. It goes, higher here and then lower in the vicinity of the bubble on both sides of it. And it, again resumes its transport after it gets away from the bubble. But the bubble itself makes phonons scatter more and therefore lowers the heat flux. And then then these planes inside of the bubble are showing the heat flux inside the xenon bubble. So larger heat flux in the center, and then around the edges where the scattering taking place, they're decreased as well. And we'll get to a little bit better view of that in a second. But this is sort of, we use that thermal interface resistance model I was talking about, the diffuse mismatch model, to show how there's a temperature difference, there's a slip across that xenon bubble itself. And this is sort of a little bit better view of it. So this isn't really showing us any scattering phenomenon, but what's happening is that it's important to understand how geometrically how this looks compared to the rest of the material. And so we have a cold to hot, a bubble that goes from cold to hot, and then here we're just able to see, and I didn't assign the temperatures to this, but this is just to show off the geometry of it. It kind of shows how the bubble's heated in relationship to its surroundings. Now, continuing on this thermal interfacial stuff, I mentioned that we use this TRISO fuel in a lot of the new reactor designs for its fuels, microreactors especially. And this TRISO fuel is layered, and it's got layers of carbon and pyrolytic carbon that contain this kernel of uranium dioxide, and those are there to help. Number one, as a barrier to fission products, we don't want to have, as we're fissioning uranium, we don't want to have, free floating or free forming fission products. So we protect against that with silicon carbide, pyrolytic carbon, and graphites. But we want to be able to see what the heat looks like across this thing, okay? So in this graphic here, you're seeing that it's actually inverse a little bit. you see heat flows more easily around the outsides of it compared to right through. It goes through the layer. It actually goes through the layers all right. And up here is sort of a cross-sectional view of what a triso kernel might look like. We can also do things. One interesting thing that people try to do geometrically is actually just add pores to materials, and so we can simulate how heat moves through this is actually just silicon. We can simulate how heat moves through silicon. If there's not just some neat little. Let me start over here. If this were at the macro scale, the engineering scale, you'd see a very smooth transition from hot to cold across this. But instead, you see some interference here in between the pores, and same with the heat flux right here. So there's some interesting phenomena that happen at this low length scale with regards to heat flux and temperature. And this is where we're getting into, why we want to model heat transport in UO2 with xenon is that when you look at geometric effects like how close atoms are to each other, if they're in the middle of a coalescing event where they sort of come together and change energy and then change shape, it all affects the heat flux and all affects phonon scattering. In this particular example, if we look up here at the upper right-hand corner, this is a slab of graphite that has tiny, tiny carbon defects in it. And I wish I would have done a little bit better for this presentation, but if you see these tiny black dots, those are concentrated carbons inside of a graphite block. And this video here is just a fly-through, and it's showing a plane that moves from one end to the other end, and it shows how the heat flux changes due to phonon scattering at these defects. So we're starting here. We're going. It's about to hit a defect right here. You can see how the heat flux changes and decreases, and it's increasing in the bulk. And then as it approaches the other defects, it also decreases. So this is some work that was done about 8 years ago for looking at phonon scattering inside of graphite. And a lot of this work was actually kind of feeding into graphene. So this is something that this is how Nate and I started talking. This is a picture of heat flux in UO2 and xenon at a bubble or at a cluster of bubbles. And once he saw this, that's when we started talking about, well, hey, what can we do to demonstrate this better? Because I thought this was okay, but Nate was able to do some really unique work with this data set and make a movie and make a bunch of cool pictures that described sort of how heat flux, the heat flux vorticity, or how heat flux moved right around in the vicinity of these bubbles. And I'm going to get into that now. So this is a still, but this shows how heat moves around the xenon bubbles itself, and how it sort of follows the contours and how it changes, follows the contours and the changes around the bubbles itself. And now, though, I want to show the movie he made, this kind of flyby of the UO2 cell with the xenon. So this is what Nate did. And this is all happening in steady state. This actually isn't this is not time dependent. And you're seeing here, as we move through the material, we see how the heat flux changes its contours around the bubble cluster itself. And what it allows us to do is to pinpoint directly, where exactly is it happening? Because obviously there's tons of intersections in this thing, and we can see now precisely where those intersections, how the intersections affect the way heat transfers. So, there is a lot of drag on the outsides of this thing, and there's not a whole lot of stuff there's not a whole lot happening at the base because the heat's coming from this side, and so there's not a lot of stuff that's happening on the back side of this thing. So obviously, directionality is involved, but we see that it hugs the contours pretty tightly, which you might expect. But it's important to say, if I just showed off some data that said, okay, well, thermal conductivity decreases in UO2 when xenon's present. All right, that's cool. But what does it really mean? What does it look like on the inside? And how could the effect be used in a positive way to develop materials that maybe might use this to their advantage? one example that comes to mind, excuse me, is in a thermoelectric material where we try to decrease, or sorry, excuse me, we try to increase the phonon heat. We increase electronic conductivity and decrease phonon thermal conductivity. All right, we want to have essentially something that insulates, but can also have a good electronic conductivity. And so if we add in defects to a thermoelectric material, we can add essentially defects or scattering sources, right? And defects decrease heat flux. So if we know where to add these things in and know how heat moves around these defects, we can preferentially tailor the behavior of the material to the defect presence itself. So we can reduce thermal conductivity in a material by adding more defects, but while we keep the electronic conductivity high. And that's sort of that's part of one of the goals here. So, we've talked about microscale heat transfer, and the goal is, and again, this is kind of high level with a lot of examples, but I wanted to try to communicate the best I could that, there is this gap in between the atomic scale and the engineering scale. And filling that gap is really important because you can't just, you'd think that like, all right, well, I've got thermal conductivity in this box of atoms. Why can't I use that thermal conductivity in a nuclear reactor? Well, there's a scale difference and it changes. And as I showed earlier with the example with silicon, the size matters. The size and the length and the dimensions of the material matter very much to how heat moves. And so knowing these things, you can actually predict phenomenon better at the macro scale by using information from the atomic scale. Secondly is that, I really want to emphasize the importance of interlaboratory collaboration. I have just been thrilled with my work with Nate. I plan to work with him in the future, and I recommend him to all my colleagues for if they need any kind of visualization stuff done. And I really am thankful that I work at a place that has resources like this that I can interact with. And I had no idea until a couple months ago, and now it's just like one of the best things ever. But that is to say that, the goal of our work in the end, we want to keep we're trying to keep the public informed. We want to keep our country safe and we prosperous. We want to, personally, I'd like to see more clean energy, more nuclear power out there. And being able to communicate these things effectively with the public through graphical examples is really great. And it's a way that we can continue our ongoing success with, campaigning for nuclear energy. And as a parting shot, this is Latch on the left-hand side and Virgil on the right-hand side. They're my coworkers at home. So thanks very much for paying attention. I hope I didn't put too many of you to sleep. And if you have any questions, feel free to ask them now.
So if you have questions, you can ask Jackson here. John Russell has a question.
Hi, thanks for your talk. I thought it was really neat to see the Boltzmann methods. I was curious, are you able to capture crystallographic direction in your simulations? And does that play any role? Does it matter?
Yeah, so what we'll do is, when the material properties get generated for us through DFT or MD, they'll come to us in 100, 111, 010. Like they'll come to us in the direction. So we can't currently. It's not really like a live thing. We don't do it live. They're generated a priori and then given to us to simulate. So a lot of the work, like for instance, that graphite was done 111. I think the UO2 was as well. But you can. It's just a matter of having the data generated for you in those directions. Yeah. But it's not real time. We're not. Eventually, I would like to, have data sets of all those three. I don't think. Well, I just know we can't do that currently. No. To link those together.
Very interesting. Thank you.
Yeah.
Any other questions? All right. Well, if you do have questions, you can contact Jackson. I have put his email in the chat, and I'll put it in there again. And Nate says if you have questions about the AVL or would like support with visualization, he has also put his email in the chat. If there are no more questions, I think we'll adjourn today. The recording will be available as well as the transcript. And so if you're interested in that, you can contact me. I'll put my information in the chat, or you can contact Matt Evans. But I just want to thank Jackson for being here today and for telling us about his work with CAES. And yeah, I hope to see all of you soon. And there's Latch. Thanks so much, everyone. I'll stick around in case anyone needs anything. Otherwise, have a great afternoon.
All right. Thanks again, everyone. I appreciate you coming in. And thanks, Hillary.